Hello, student. Welcome to this chapter, Astrophysics. I'm going to continue this chapter, Astrophysics. So, in this class, now we are going to study the stellar parallax. We'll see what is the stellar parallax, and before that, we will see what is the parallax. What is the parallax? Here, I have given two examples. You can stand nearby a tree and watch at any specific area of the stem. Here I have shown a tree here. This is the stem of this tree, and you can watch somewhere here. Now you close one eye and see the stem of the tree. Then close the other eye and see at the same place. That means you are looking at here. So now you close your one eye and you are looking at the other eye at this place, and then reverse it. That means close this eye and open this eye, and with the help of this eye you look at this point. This is what you have to do. You will feel that stem or tree is shifting from one place to another. It is called as the parallax. That means when you do this one, what you will find is that this tree is there. You will feel that the stem of this tree is shifting, is displacing from one place to another place. This kind of feeling you will see, and this phenomenon is called as the parallax. Another example is that hold a pencil near to your nose vertically up. Here I have shown pencil. This is a pencil, and you hold this pencil near to your nose and look at the top of this pencil through your eyes. So what happens, you see, hold a pencil near to your nose vertically up, then look at the tip of the pencil with one eye closed. So this is the tip of the pencil, and you are looking at the tip of this pencil with one eye. This eye, let us say this eye is closed. Then look at the tip of the pencil with one eye closed. Repeat with the other eye closed, and that means again you close this eye and look with the help of this eye, and again what you will see that the tip of this pencil is shifting. So this is the apparent shift. Initially you will feel that the tip of the pencil is here, and when you suddenly switch over to other eye, you will feel that the tip of the pencil is here. This is called as this is due to the phenomena of parallax. So therefore this kind of phenomena we can make use of some else something to determine in the physics. So I was here. Then look at the tip of the pencil with the one eye closed. Repeat with the other eye closed. What is felt is that the pencil is shifting its position. Actually, it is not shifting. So this is the apparent shift. So this is called as the phenomena of parallax. So in this experiment, what we observed is that move the pencil away from you and check for parallax. It is found that shifting is less. That means initially the pencil was near to your nose and you have checked the parallax. Then move the pencil away from your nose, then check for the parallax. It will be very less. Even at a certain distance from your nose, there will be no parallax at all. So this is what you observed. So therefore, closer the object, more will be the shifting or parallax phenomena, and farther the object, lesser will be the parallax. So this is the outcome of this experiment. So this phenomena could be used to determine the uh, uh, distances to determine the distances of distant objects without actually measuring the distance, and that is called as the trigonometric parallax method. This method is called as the trigonometric parallax method. So this trigonometric parallax method was initially used by land surveyors who were working in the fields to determine the various distances, which are generally better distances of higher magnitude. So here, so land surveyors use the technique of triangulation to measure the distance of farther objects. Suppose that we have to determine the width of the river. So in this diagram, I have shown a river. Let us say you are in this end of the river, this side of the river, and you have to measure. So one tree is there on other side, and you have to measure the width of the river. Suppose that we have to determine the width of the river. For that, a appropriate line is drawn at one side of the river, which is called as a baseline. So you can see here a line is drawn here, which is of 2b, which is of magnitude 2b, and this is called as the baseline. From one end of the baseline, a tree, say, at other end of the river is seen through an equipment, and a reading is noted down. So initially you are here at this point of the baseline, and you are looking at the tree which is on other side of the river. Some equipment is there. Surveyors use a particular equipment. I have forgotten its name, and they will note down some reading by standing here at one end of the baseline. So then move to the other end of the baseline, and the same tree is seen through the equipment, and reading is noted down. So then what happens? You are moving to the other end of the baseline, and you will stand here, and you will look at the tree again, and you will note down the second reading. So that what happens, then move to the other end of the baseline, and same tree is seen through the equipment, and its reading is noted down. The then triangulation is done to complete the triangle. From the right triangle ACD, we can write tan P is equal to B divided by D, or D is equal to B divided by tan P. I will explain what are these the things here. So triangulation is done to make this a triangle to complete this triangle. So this is the baseline. AB is the baseline which I have shown here, which is of length 2b. So that length 2b is divided into 2. So it is b, and it is b. B plus b is 2b, and this is the vertical distance between the tree and midpoint of the baseline, that is denoted as a D. And this length of the baseline, that is AB, AD subtends an angle P at C, and this angle is called as the parallax angle. This angle is called as the parallax angle. So from this right angle triangle ADC, from this right angle triangle ADC, uh, this AD, half of the baseline AD is known, and I want this D, which is the distance between two sides of the river. So I can apply the trigonometry easily, and from trigonometry tan P is equal to opposite side divided by adjacent side. So here opposite side is B, half of the baseline, and adjacent side is CD, that is D. So therefore, you want to calculate d, the distance. So therefore, you are writing this equation as distance d is equal to b divided by tan p. Huh? So where p is the parallax angle. In a simple way, in this a simple way, you can measure the longer distances without actually measuring it. So this is the indirect measurement. Hmm? So therefore, the distance d of the object can be estimated easily using our equation. This p is called as the parallax angle. Farther the object, smaller the parallax angle. So if the distance, if that means if the object is very far away from you, then the parallax angle will be a lesser one. If the object is very far away from the observer, then this P is very small. The parallax angle P is very small, and the above equation becomes D is equal to B divided by P, because angle when the angle P or theta is small, tan theta or tan P can be simply written as a P as per a small angle rule. So therefore, that above equation becomes simply like this. That is D is equal to B divided by P. So using this equation, we can determine the distances of a farther object without actually measuring it. This is called as the parallax method. And this parallax method can be extended to measure the stellar distances. The stellar distances are where generally distances, huge distances, which are in terms of thousands of kilometers. So it is not possible to measure the distance of the stars by direct method. So we have to follow some indirect methods, way of determining the distances. So this trigonometric parallax method is used to determine the distances of the stars. Let us see how it is done. So this trigonometric parallax method could be extended to determine the stellar distances. As the distances of the object increases, the length of the baseline increases. So this is a very important phenomenon. So I told here what is the meaning of the baseline. So this is the baseline. When you observe an object, distant object, before that you will have to draw, or you will have to choose a sufficient or the proportional amount of a baseline. So, but what happens as the distance of this distant object increases, the length of the baseline increases. So that is the main problem of this method. And now we are going to have to measure the distances of stars. You can imagine how the length of this baseline increases. This length of the baseline increases tremendously. So it is very difficult to draw such a big line. So we have to do some other ideas. So this is a very important point. As the distance of the object increases, the length of the baseline increases proportionally. Therefore, to determine the stellar distances, a baseline of very large length is required. Even the diameter of the earth is not enough. That means you may think that the earth is sufficiently a huge body, so its diameter could be taken as the baseline. So by standing at one end of the diameter you can make one measurement, and by standing at the other end of the diameter of the earth, you could be do the second measurement. But when you deal with the stars and the stellar distances, this baseline is again not is of no use, because it is a smaller one. It is a smaller one because the stellar distances are very very large, larger quantities. So, a baseline of very large length is required. Even the diameter of the Earth is not enough. Thus, the diameter of the Earth's orbital around the Sun is used as the baseline for measurement. So, as the diameter of the Earth is not enough, now we can choose the diameter of the orbit in which or along which the earth is rotating around the sun, so that we can make use of. In the diagram I have shown here, sun is here, this is the earth, this earth is rotating around the sun, so this is the orbit, this is the orbit of the earth. So we are thinking that this orbit is a circular one, which is actually not exactly a circular one, but just for approximation, I will think that this orbit is a circular one, and the diameter of this circular orbit is like this. So in this experiment, at one position of the Earth, the telescope is focused to a nearer bright star in the background of fainter distant stars, like this. So here, now you think that your Earth is here at this end of the orbit, and you are looking at stars, and you have to choose a brighter nearer star. Let us say this star is a nearer one, and this star is observed in the background of distant stars, which are fainter generally. They may not be fainter by that means it does not mean that the stars are fainter means it does not mean that they are less luminous. The stars may be at a higher distances, because of that reason also sometimes they looks a little bit fainter. And what happens, these distant stars appear as if they are stationary, they are stationary. So you are looking at this nearest star only, earth is here, and you are making one reading, and you are taking one reading. Next, the telescope is focused to nearer object, nearer bright star in the background of fainter distant stars, and a reading is noted down. Next, exactly after 6 months, the Earth moves to other extreme end of the orbit, and the telescope is again focused to the same star, and a reading is noted down. So what happens? The reading has to be taken at the other end of the baseline. Now this is the baseline. So you have done the measurement at this end of the baseline, and you have to take a reading at the other end of the baseline. That means you are moving, earth is moving, so you have to wait until the earth comes here to this position. So the time taken by the earth to move this position is 6 months. So it takes exactly 6 months to come to this position. So for that you have to continuously watch this star, and you have to wait. And once the star comes to this position, the observer is taking the second reading. So exactly after 6 months, the Earth moves to the other end of the orbit or the baseline, and the telescope is again focused to the same star, and a reading is noted down. So using the method of triangulation, a triangle is completed. As I explained earlier, triangulation method is used to make to complete the circle to complete the triangle. So the diameter of the Earth's orbit is roughly equal to 2 astronomical units. So here I have shown. So this is the diameter of the Earth's orbit. It is roughly 2 equal to 2 astronomical units. That means half of this. That means the distance between Sun and Earth. This distance is 1 astronomical unit. And similarly, the distance between Sun and Earth when Earth is here is again 1 astronomical unit. So that distance is taken as 1 astronomical unit. So the diameter of the Earth's orbit is roughly equal to 2 astronomical units. That means the distance between the Earth and Sun is roughly 1 astronomical unit. So when the Sun and Earth are at this distance, that is 1 astronomical unit apart, they subtend an angle P at the star. This parallax angle is taken as 1 arc second. So what happened? You have completed the triangulation process. So a triangle is formed here. A triangle is formed here. So in this triangle, you choose this right angle triangle. In this right angle triangle, so this distance is known. That means the distance between the Sun and Earth is known, which is 1 astronomical unit. And the this distance means the distance between Sun and this star is to be determined, that I have taken as d. So this length of 1 astronomical unit subtends an angle P at the star, and this angle is called as the parallax angle, and this parallax angle is measured or expressed in terms of arc second. So when the distance between the Sun and Earth is 1 astronomical unit, then the angle subtended by this distance at the star is taken as a 1 arc second. This angle is taken as a 1 arc second. So that is the meaning. So that is the meaning. So you are come back to this point. That means the distance between the Earth and Sun is roughly 1 astronomical unit. So when the Sun and Earth are at this distance, that is 1 astronomical unit apart, they subtend an angle P at the star. This parallax angle is taken as a 1 arc second. I will explain what is this 1 arc second. Actually, this angle, this parallax angle, could be measured in terms of radian also or degree also. But this angle is very, very small. So because of that reason, that is expressed in terms of 1 arc second. Then the distance between the Sun and the nearest star is taken or defined as a 1 parsec. So this is another definition come this in this chapter. So that means the distance between the that is Sun and that nearest star is 1 parsec. When when the parallax angle subtended at the star is 1 arc second. Hmm? When the subtended angle is equal to 1 arc second, then the distance between that star and the Sun is taken as a 1 parsec. So this is the standard definition. So, thus, by trigonometry, you are completing the triangle. So, from the triangle, tan p is equal to 1 astronomical unit divided by d, because tan p is opposite side divided by adjacent side. Opposite side is the distance between sun and the earth. So, that is the 1 astronomical unit. And this d is the distance, the vertical distance between the sun and the star. So therefore, from this equation, you can calculate d is equal to 1 astronomical unit divided by tan p. So here, since the distances are very large, this parallax angle is very, very small. So because of that reason, so this tan p is written as a simply p. So that is when the angle is small, tan p, tan theta is written as a theta. So that idea is used here. So this becomes d is equal to 1 divided by p, and AU means astronomical units. So the parallax angle P is measured initially in radians. As this is the, as in this present case is very small, it is expressed in terms of arc second as below. So one radian is equal to actually 57.296 degrees, and this degrees is converted into seconds. So this much of seconds you will get, and this is called as the arc second. So that means one radian is equal to this much of arc second is expressed. So therefore, the our equation becomes d is equal to 2066265 divided by p double dash in extra units. So this parallax angle is written as p double dash. So that indicates that this parallax angle is in terms of arc second. But one parsec is equal to 1 divided by 206,265 astronomical unit. So therefore, this equation you can write as d is equal to 1 divided by p double dash in terms of parsec it is. PC means a parsec. So then you can express this thing in terms of in terms of the another unit called as the 1 light year. So it is, as you know, it is the 1 light year means it is the distance traveled by light in vacuum in 1 jubillion year. 1 jubillion year means it is 365.25 days. So therefore, what happens? 1 light year is equal to 9.461 into 10 power 15 meter in terms of meter, and 1 parsec is equal to 3.262 light year. So our equation can be written as d is equal to 3.262 divided by parsec, divided by result parallax angle in terms of light year. So this equation is in terms of light year. So I have one example uh, uh, for just for one star. In 1838, after 4 years of observing this 61 Cyane star, nearer star, actually Sun is the closest star, and the next closest star is this Cyane. This Cyane was observed by this vessel for a long time, 4 years. So announced his measurement of a parallax angle of 0.316. So he estimated that the parallax angle for this star is this much, and calculate the distance of the star. So we can calculate in this way. D is equal to 1 divided by p double dash parsec, because here the parallax angle is in terms of arc second. Sorry, this parallax angle is in terms of arc second. So we have to use this equation. So d is equal to 1 divided by p double dash in terms of arc second, in terms of parsec. So you just substitute the value of this arc angle, parallax angle, which is in terms of arc second. So you put here and you simplify here. So it gives a 3.16 parsec. That means the distance of the star Cyane 61 Cyane is is 3.16 parsecs. Or you can express this in terms of large year, it becomes 10.3 light years. And or you can express this distance in terms of meters, then you multiply by 9.5 into 10 to the power 15. So it gives 97.85 into 10 to the power 15 meters. So the distance of this stars 61 Cyani is this much. Simply it is calculated. It is the approximate one, not the accurate one. So this size 61 Cyani is the next nearest star to us, apart from the sun. Sun is the closest one. So this is the about stellar parallax method, and you carefully read it carefully. It can be asked in the examination. Thank you for the listening.